This week we're going to be looking at vectors. The world that we live in is full of pushes and pulls. You might have a force that is pushing in one direction, or you might have a force that is pulling in another. That's just one application of vectors. If you've taken physics or if you plan to take physics, this is something that you're going to see a lot. So a vector is a quantity that has both magnitude and direction. And my favorite thing to look at, this was one of my favorite things that has ever come out. If you've ever seen the movie with the Minions, why can't I think of what it's called? With Gru, Vector is the villain in the movie. Despicable Me. And he calls himself Vector because he commits crimes with magnitude and direction. And that is exactly what a vector is mathematically. So for example, if you're driving due north at 50 miles per hour, then the magnitude is your speed that is 50 miles per hour. The direction of that motion is due north. So speed has no direction. You can drive 50 miles an hour in any direction you want. But if you make it a vector, you say that you're driving north, and that adds a level of description that a regular number, which we call a scalar, like 50, doesn't have. So that's the value in using vectors. So like I just said, a quantity that has magnitude, so it has value but no direction, is called a scalar. So a scalar is just a number, like your height. You just have a number that is your height, or you have a number that is your weight. The direction doesn't matter with that, okay? So we're going to look first at vectors in the geometric sense. So you may have seen this in geometry. We called it a directed line segment. If you don't remember that, that's quite all right. It's a directed line segment because it's been assigned direction. It has an initial point, which is a dot, and it has a terminal point, which is going to have an arrow on it. You've seen this before. These are rays from geometry, okay? In geometry, though, when we talk at a ray, that arrow means that it goes on forever. That is not actually true with a directed line segment. The arrow is only symbolizing direction, not that it goes on forever, because a directed line segment is finite. It starts and it stops, okay? So the magnitude of a directed line segment, aka a vector, is called its length. And so to signify magnitude, we use these double bars on the outside. So if I see that double bars around the vector PQ, that tells me that basically I want the distance from P to Q. And since distance is never a negative value, a vector cannot have a negative magnitude. It could have a negative direction, but its magnitude will always be positive. Okay, so when you see vectors typed, you're always going to see they're usually written in bold print. However, we can't really bold our printing, and so we put the arrows on top, kind of like when you did a ray in geometry. Now, I learned that it was different than a regular arrow. So the way that you'll see me write it is like if I wanted to write the ray PQ, I would write it like this in geometry. But if I wanted to write the vector PQ, I write that like this. That's how I learned it, is kind of like this hook arrow at the top rather than an arrow. That way you don't get confused. So that's what you'll see me write. It really doesn't matter. It just needs to have an arrow on the top. And so that's the way that we would print it with our handwriting, since we can't really do bold handwriting. Okay. Now, equal vectors are going to be vectors that have two things in common. They have to have both the same magnitude and the same direction. So this first example, V and W are equal because they're both going the exact same direction and they have the same magnitude, the same length. V and W appear to have the same direction in this second example. They appear to have the same magnitude, but they are not going the same direction. So V and W would not be equal there. Similarly here, in the third example, we can see that they have the same magnitude, but One is going kind of southeast and the other is going sort of northwest, so those are also not equal vectors. And then D, we can see they're going the same direction, but they do not have the same magnitude. So the only case where we can say that V equals W is this first one here, okay? They have to be the exact same direction and have the same magnitude. So let's look at a couple of examples. When we are looking at these two, okay, so it does appear in this case that U and V are equal, but if we want to be able to mathematically prove that they are equal, then we need to show two things. We need to show that they have the same direction and magnitude. Now, direction we're going to think of in terms of slope, and then magnitude, like we said, is going to be distance. So we're going to use Pythagorean theorem or the distance formula to think about that. So in order to show that they have the same direction, let's consider the slope of vector u. And so we can see on this one that we have a rise of 4 and a run of 3. So the slope appears to be 4/3. If we look at the slope of vector v, we see the exact same thing, up 4 over 3. So they have the same direction. Check. Now magnitude is basically the distance, and you can use the distance formula, but the distance formula is just the Pythagorean theorem. So I look here and I have 3 and 4 as my sides. So the magnitude of vector u, which we again use those double bars for, is going to be the square root of a squared plus b squared, because we're basically solving for c, Pythagorean theorem. So we're going to have 4 squared plus 3 squared. And you may recognize that one as a Pythagorean triple, 3, 4, 5. And we can see with v that we're going to have the exact same thing. The magnitude is going to be the square root of 4 squared plus 3 squared, which is also 5. So they do have the same distance. And so now we have shown that u and v are equal to each other. And that's that. Now, a vector can be multiplied by any real number, which would be a scalar, and all it does is it multiplies the length. So for example, if we look here, this first one is just v, so this is kind of our base vector that we're going to use. 2 times v would just double the length. I have basically 2 of the v's here. Half of v would cut its length in half, -3 halves. When you multiply by a negative, notice that it changes the direction. Here's the initial point, and here's now the terminal point, where originally it went the opposite direction. So that's what multiplying by a scalar does, is it changes the length, the magnitude, and it changes the direction. Now, we're going to look at how we can add and subtract vectors geometrically. So on a picture, the image shows a geometric method for adding 2 vectors. The sum of u and v, which we would just write as u plus v, is called the resultant vector. That's your answer, is the resultant vector. So the way that you geometrically add vectors, so like on a picture, is you're going to take u and v and you connect them dot to arrow, dot to arrow. So I start with this first one. If I'm adding u is right here. So I start with the dot of u and I go to the arrow of u. And then when I draw v, I start with my dot where the arrow was for u. And then I draw my vector v. The resultant vector goes from the very first dot to the very last arrow, and that's how we determine u plus v. And we're going to look at a picture of this here in just a second. So I want to skip ahead from subtraction just for a moment. Let's look at example A here just to kind of illustrate that. I want to add PQ, the vector PQ, plus the vector QR. So if we look at that on this diagram that they gave us, okay, first PQ. Now again, the direction matters. So here's our dot at P, and we're going through to Q. That's where the arrow is going to be. Then we want to add to that QR. So that means the dot at Q and the arrow at R. Now this is set up exactly how we want because we've gone dot, arrow, dot, arrow. So that means that our resultant vector starts from the first dot and points towards the last arrow. So the answer would be the vector PR. And the order you write it in does matter because it always has to go dot, arrow in that order. Okay, so that's how we would add them. Subtracting is a little bit trickier. If I want to do V minus U, that's basically going to be the same as V plus negative U. So if I have U and V right here in blue, okay, and I want to do, here's V, this is the original, and here's U. And I want to do V minus U, okay? The first thing that I need to do is I need to get them dot to arrow. So that would move U up to here. And then because I want to add a negative, that's going to flip it the other direction, which is where this comes from. And now, just like with adding, we're going original dot to final arrow. And so that's why this pink one ends up being the answer there. Now here's sort of a simpler way, if you want just kind of a step-by-step of how to remember that. First, when we subtract, we actually want to connect them dot to dot. So when we added, remember we wanted to connect them dot to arrow. But this time we want to connect dot to dot. And then the way that you find your final answer is that we draw that out. And when you do dot to dot and then you connect the two arrows, so the answer would be right here. Okay, where you decide to give it direction if you're doing V minus U. Now, if you do U minus V, the order would be backwards. So the arrow of U, which is where you ended up, because that's the second part, that's the thing you're subtracting, points towards the arrow of V, which is what you started with. So the you connect from the arrow of U, which would be right here, and you point towards the arrow of V, which would be right here. Now, even though this is in a different spot than this one they drew there, remember that as long as they have the same direction and magnitude, they are equal. The location of the vectors doesn't matter when we're talking about whether or not they're equal. Okay, so subtraction is a little bit weirder. So let's go ahead and, remind me later. Let's go ahead and finish this example here. So we already did example A. Let's look at example B. Maybe go ahead and pause me for a second and see if you can come up with the answer for that one. Try one yourself. So if we want to do RP to PS, we need to think R to P, so the arrow is this way, and then P to S. So this one is connected dot to arrow. So my answer is original dot to final arrow. So that would be the vector RS. Okay. Now subtraction is always, for me at least, the trickier one. Okay. So if I want to do QS minus PS, here's what we have so far. QS would be this way, minus PS, which would be this way. Now, this is not set up how we want it because right now these are pointing arrow to arrow. To subtract, we want them to be dot to dot. So I'm going to recopy PS so that it goes same direction, same magnitude over here, kind of like that. Okay, so I just shifted that vector over. So since PS is the one that we are subtracting, that's where our dot goes. and our arrow goes towards the arrow of QS. So that would be like this, which is the same as this one. Okay. So QP is the answer there. Now this last one, you really can only add in pairs. So we just have to kind of go one pair at a time. So I'm going to start by getting this answer. And then whatever answer I get here, then I need to add that one to PQ. So again, as a final check, pause the video and see if you can come up with that answer before you listen to my explanation. So for RS, that's going to be this guy to this guy, and then SP is here. So that answer is going to be RP. Now, we want RP plus PQ. So our final answer then is going to be RQ. And that is how we can geometrically interpret what we know about vectors.